Good morning, everybody, and welcome to this fourth lecture. So, today's topic is for integrals and residues. So, last time we've seen the residue theorem. This is a theorem in which we can express the integral of a holomorphic function along a contour in terms of the residues or the singularities that this holomorphic function has in the region bounded by the contour. And today we'll see how this theorem can be used to compute integrals of functions defined on the real line. So let me first recall the residue theorem. So we have a function, a holomorphic function f on some domain U. This is our domain. And inside U we have a contour. And the region are bounded by the contour is contained in U union. There are some points missing from U. F has some singularities inside, so it has possibly some singularities in the region bounded by the contour. These are the points Z1 to Zk. And the residue theorem tells us that the integral of f along the contour gamma is 2pi times the sum of the residues, residue f z dot, where dot goes from 1 to k, and z1, zk are all the singularities that are contained in the region bounded by the contour. Okay, so we have a formula which allows us to express an integral along a contour in terms of residues. And residues, of course, are easier to compute than integrals. One has just to study locally the function f near the singularity. We have seen couple of formulas allowing us to compute residues. Okay, and in order to see how this method works, let's start with an example. So our example 1 would be compute the integral from 0 to 2p of the function 1 over a plus b cosine t in dt. Where here a and b are positive numbers, more precisely a is bigger than b, which is bigger than 0. Okay? So we have this real valued function on this interval 0p of the real line, and we would like to compute its integral. So first of all, notice that the condition that a is bigger than b, and positive, guarantees that the denominator here is always positive. So it never vanishes in particular, so we are actually integrating a continuous function on a bounded interval, so this integral is for sure well defined. And in order to compute this integral, so now we would like to, so this is an integral on an interval of the real line, so if you want, okay, you can see it in the complex plane, but then it will be an integral on an open curve, not on a closed one. But here we can use the fact that cosine is actually a 2p periodic function and see this integral as an integral on a contour. More precisely, if we set z to be e to the I t, with t real, then cosine of t, so cosine of t is the real part of e to the I t, and the real part of a complex number can also be written as 1/2 this complex number e to the I t plus the conjugate of the same complex number, so e to the minus I t. And now this is 1/2, e to the I t is z, and e to the minus I t, since this is a complex number of modulus 1, we can think of this as plus 1 over z. Okay? So we could also write here, of course, z bar, but I want to write 1 over z because in this way here I see a holomorphic function of z. If I would write z bar, then this would not be a holomorphic function. Okay, so we have this well-known formula. The cosine of t is 1/2 z plus 1 over z, when z is e to the I t. And then we can use this as a substitution in this integral. So we compute this integral by making use of this substitution. So if z is e to the I t, then dz is I e to the I t dt, which is I z dt. Or in other words, dt is dz divided by I z, which we can also write as minus I dz divided by z. Okay, and then our given integral 0 to p 1 over a plus b cosine t dt. So if we make this substitution, this becomes 1 over, so a plus b. Instead of cosine t, I use this formula. So I have b half z plus 1 over z. And then dt becomes dz divided by z, and there is a minus I multiplying everything, which can go outside the integral, so it comes here. And now the integral, so t was varying between 0 and 2p, the interval 0 to p. This means that now z, e to the it, varies on the unit circle centered at 0. So this is an integral on the contour k01. Okay, so unit circle centered at 0, and on which we run, as usual, counterclockwise. Okay, so we have to compute this integral. So maybe we can just manipulate the expression to get a better formula. So we can multiply everything by numerator and denominator by 2. And so here we get minus 2I integral, in this case 0, 1. 1 over, and here if we multiply, so we're multiplying everything by 2, and then we're also, now we multiply by z, and we obtain b z squared from here. From here we will get a 2a z, and here we get a plus b in d z. Okay, so this is the integral we are interested in. And as you see, now we have exactly the integral of a holomorphic function, this is a rational function, on a contour. So we can apply the residue theorem, and we have to see, we have to look for the singularities of this holomorphic function. So this is a rational function, so the singularities will be poles, and will be exactly, the poles will be exactly the zeros of the polynomial appearing in the denominator. So what are the zeros of this polynomial? bz squared plus 2az plus b equals 0. So its zeros are as 2 zeros, namely, so the first zero, alpha, is minus a plus square root of a squared minus b squared, everything divided by b. And the other zero is beta equals minus a minus square root of a squared minus b squared divided by b. Okay, so these are the zeros of this polynomial. Notice that these zeros are real, because a is bigger than b, so this a squared minus b squared is a positive number. So we have precisely two real zeros, and they're both actually negative numbers, and beta in absolute value is a plus square root of a square minus b squared divided by b, and this is bigger than a divided by b because this square root is positive, and a divided by b is bigger than 1 because a was assumed to be larger than b. So this equation is the following: the zero here is the unit circle, and the zero beta is negative and outside of the unit circle, while the zero alpha, you can easily check that alpha times beta is just 1. If you multiply together these numbers, you get 1. So this you could also deduce from the form of the polynomial. And therefore, alpha is in absolute value instead less than 1. So alpha is still negative, but it's here. Okay? So we have this holomorphic function which has two singularities, one at alpha and one at beta. Only one of them is in the region bounded by our contour. And so from the residue theorem, we conclude that this integral equals, so we have this number minus 2i, we can just copy it, times 2pi times the residue of the holomorphic function f at alpha, where now f is the function f of z 1 divided by b z squared plus 2az plus b. And so this we can also write as I times I is minus 1, with this minus becomes a plus. So we have a 4p times the residue of the function f at alpha. Okay, so the last step is to compute the residue of the function f at alpha. We need just a little bit of space. Maybe I'll keep just here the formulas for the two zeros of the polynomial. So the function f can also be written as 1 over, I can collect b, so this is b times z minus alpha times z minus beta, since alpha and beta are the zeros of this polynomial. So this holomorphic function has a simple pole at alpha, and we know that the formula for the residue of f alpha, in the case of a simple pole, this is just the limit for z converging to alpha of z minus alpha times f of z. And this limit is z minus alpha eats this z minus alpha in the denominator, so we have 1 divided by b times alpha minus beta. And alpha minus beta is twice the square root divided by b. Here we're multiplying by b, so this equals 1 divided by twice the square root a squared minus b squared. So this is the value of the residue, and we just plug it in here, and we conclude that the value of our integral is 2i divided by the square root of a squared minus b squared. Okay, so this is the value of the integral we were interested in. Okay, very good. This was example 1. So this example is a particular instance of a general fact. So maybe let's see what we have done and put it in a bit more general framework. So when we call integrals of this kind, we call integrals of type 1. So the integral of type 1 is something of the form, it's an integral from 0 to 2 pi of r cosine t sine t dt, where r is a rational function but of two variables. R is a function r of x and y. It's a rational function. It's the quotient of two polynomials in two variables. And the assumption is we don't want to have, so we want this function to be well defined on this interval, meaning that R has no singularities on cosine. The pair cosine sine lives on the unit circle x, y in r squared, x squared plus y squared over. Okay, so we want to integrate such a function, and what have we done? So we were considering the substitution z equals e to the I t, and if we use this substitution, then cosine of t, we have already seen, this is 1/2 z plus 1 over z. And instead, sine of t, so to take the imaginary part of this, and you obtain the formula 1 over 2I z minus 1 over z. And finally, from here, we also have the fact that dt is dz divided by I times z. Okay, and now if we apply this substitution, what we obtain is the following formula. The integral between 0 and 2I of r cosine t sine t dt. This is nothing else but 2I sum of residues of the function r star. Let me write what r star here is at zj. J is going from 1 to k, where this function r star is, so remember, here we have this 1 over z coming from dt, and then r cosine t sine t can be expressed as r of this quantity, comma this quantity, meaning that r star of z is here the holomorphic function, actually the rational function, 1 over z times r of 1/2 zima plus 1 over z, comma 1 over 2I z minus 1 over z. So this is the definition of the function r star, and zj are the singularities of the function r star that are contained inside the unit disk. Okay, so zj are singularities, and they are all poles because it's a rational function of r star inside the disk of radius 1 centered at 0. And yeah, notice that in the residue theorem we have 2pi times the residue, but we have simplified this I because we had an I here, and then which we didn't put in the definition of the function r star. Okay, so we get this nice formula. Which is general, and this formula allows us to compute all these integrals of rational function applied to this trigonometric function sine and cosine, provided that we are integrating on the whole interval 0 to pi. Okay, this method of residues cannot be used to integrate on arbitrary intervals. Here we really need to integrate over a period so that we can transform this integral as an integral over a contour. Okay, so this is type 1. Now let's go to a second kind of integrals. So now we will integrate rational functions on the whole real line. And before doing this, let me recall some basic facts about improper integrals. So, when you have a function f defined on the real line, complex values, let's say that f is, as usual, at least continuous in our case. Restriction of a homomorphic function, continuous. Then the improper integral, so the integral from minus infinity plus infinity, fx dx, is defined to be, this is the limit for a going to minus infinity, integral from a to 0, f of x dx, plus limit for b going to plus infinity of integral between 0 and b, f of x dx. So more precisely, so we say that the function f has an improper integral on R when both these limits exist and are finite, when both these limits converge. Okay, in this case, the function is said to have a proper integral. So here we have split the integrals at 0. It's equivalent. You can easily show you can split at any point. But 0 is somehow a natural choice. So this is the definition in proper integrals, and f is said to be summable when the absolute value of f has an improper integral. On R. Okay, so when you apply this to the absolute value of f, and if this happens, so if the function absolute value of f happens to have an improper integral, then you say that f is summable. And the general fact is that f summable implies that f itself has an improper integral. Has improper integral. So this is a sufficient condition for having the proper integral. It's not necessary, so the other direction is false. There are functions which have an improper integral but are not summable. And a nice feature of summability is that when f is summable, then the improper integral, so not only it exists, but in this case, instead of having these two limits, you can express it as one limit. This is the limit r going to infinity, integral from minus r to r, f of x in dx. Okay, so we can integrate on this symmetric interval centered at 0 and then let the size of the interval go to infinity. Okay, we can use this formula when we have summability. Instead, in general, if I have, it might happen that, for instance, this limit exists, but however the function does not have an improper integral. A trivial example is take any odd function, for instance, the function f of x equal x. In this case, this will be identically 0, so this will have a limit 0, but the function f of x equal x does not have an improper integral, because if you split instead the integral in two parts, both limits will diverge. So the value of this limit is called the principal value of Cauchy. For instance, in the book of Howe uses sometimes this notion of principal value. For us, it will not play any special role. We will, in many cases, we will work with summable functions. In some cases, we will also work with functions which do have an improper integral, but are not summable, but nevertheless we will not need these principal values. Okay, last thing about these improper integrals, if f of x is bounded by something like constant divided by absolute value of x to the power alpha, or x in R, with alpha strictly bigger than 1, then f is summable. Okay, this is a sufficient condition for summability. You are below 1, so constant, divided by absolute value of x to the power alpha, where alpha is strictly larger than 1. Power 1 would not be enough. Any power larger than 1 gives you summability. Okay. After this, reminding you about these facts, let's deal with our example 2. So in example 2, we would like to integrate exercises to compute the integral between minus infinity and plus infinity of the function 1 over 1 plus x to the power 4 in dx. Okay. This improper integral of this real rational function over the whole real life. So, the first observation is that this function x going into 1 over 1 plus x squared, x to the 4th, is summable. On R. So first of all, this is a nice regular function on R, because this polynomial has no zeros on R. The zeros of these polynomials are the 4th square root of minus 1, and none of them is real. And so it's a nice regular function on R, and it, at infinity, it behaves as 1 over x to the power 4. So 4 is bigger than 1, so we do have summability. Okay, so we have this summable function, and we would like to compute its integral. So of course, one way would be, so this is a rational function. Rational functions, if you have a rational function, then you can always determine explicitly a primitive of this rational function. You have to do a decomposition into simple fractions, and then according to the nature of the various pieces, you have several ways to compute the primitives of such simpler rational functions. But here the thing is that by using the residue theorem, computing integrals over the whole real line does not require actually finding a primitive of this function. We will get the result also without finding this primitive. And in this case, what we would like to do is the following. So we will integrate over a half circle. This goes from minus r to r, and this is a half circle of radius r. So we will call this contour gamma r. So this contour has two pieces, the interval minus r, and then this half circle, let's call it SR. So SR denotes this curve here above. So notice that our function 1 divided by 1 plus x to the 4, so it extends as we can consider its holomorphic extension to C. This is the function 1 plus 1 over z to the 4. And this is now a rational function, so it's a holomorphic function on C minus the poles of this rational function, namely the zeros of the denominator, and the zeros of the denominators are the fourth roots of minus 1. The fourth roots of minus 1 are, so this is C minus, so let me draw the four. This is the unit circle here. One is here, one is here, one is here, and one is here. These are the fourth roots of minus 1. So they are e to the t over 4i. This is this root. And then we have this one, e to the 3 over 4 p I. This is this one. And then we have minus this one, so minus e to the I over 4 I, and minus this one here, e to the minus 3 over 4 p I. Okay, these are the poles of this holomorphic function. Notice that only two of the poles are in the region bounded by the contour, the two outer ones. Let's go back to the contour. This contour consists of this integral, from minus r, and this will give you, so integrating on this interval will give us a piece of the integral we are interested in. And then we have also the integral over this circle. What I claim is that the integral of f of z dz on SR on this half circle goes to 0 when r goes to infinity. And this can be proven by using, so we will use the standard, so in order to compute the integral, when we have to compute the integral of a function f of z dz on some path gamma, we have this standard estimate. This is less or equal than the maximum of the absolute value of f composed gamma, or if you want, the supremum norm of f over the curve, times the length of gamma, the length of the curve. We have this standard estimate for line integrals. So what happens if we apply this standard estimate here? So notice that the function f has a bound of the form f of z in absolute value is bounded by some constant times z to the power 4. Okay, this you can easily find from this expression. So we have this bound, and say for z large, in absolute value large, and therefore, when we integrate f over this half circle, and we take the absolute value, here we have, so the function f in absolute value on this half circle is smaller than c times r to the power 4, and the length the length of this half circle is pi times the radius. So we have the bound c pi divided by radius to the power 3. And this goes to 0 when r is going to infinity. Okay? So this shows that the contribution of the integral given by the integral of this as r goes to 0. And the conclusion is that the integral, if we do the integral on the whole contour of f of z dz, contour gamma r, so this integral will split in two parts. One is the integral from minus r to r, and this we can write it as, this is the integral we're interested in. This is the integral will be 1 over 1 plus x to the 4 dx, here, plus the integral on SR f of c z. And when we, so this formula holds for every r, and when r goes to infinity, this converges to the quantity we're interested in. This converges to the integral from minus infinity plus infinity, 1 plus x to the 4 dx, and this instead goes to 0 for r going to infinity. Okay? And this means that if you want to compute this integral, it's enough to compute the limit for r going to infinity of this integral. But now this is an integral on a contour, and actually its value is independent of r whenever r is so large that we have included all the singularities in the upper half plane, namely whenever r is bigger than 1. So what we obtain, we can now use the residue theorem. By using the residue theorem, we obtain that the integral we are interested in, minus infinity plus infinity, 1 divided by 1 x to the power 4 dx, this equals the integral over gamma r of 1 plus c to the 4 dz, and this equality holds whenever r is bigger than 1. Okay, because here we have to write actually the limit for r going to infinity, but all these integrals have the same value whenever r is bigger than 1. And this integral can be now computed using the residue theorem. So this is 2 pi times the residue of the function f at this pole, e to the pi over 4 pi, plus the residue of the function f at this other pole, e to the 3 over 4 p I. Okay? So in order to compute, to finish the computation, we just have to compute these two residues. And these two residues, so these are residues at simple poles, so you can use the usual formula. And I will write down here what the values are. The residue of the function 1 plus e to the 4 at e to the pi over 4 I has the value 1 divided by 2 I square root of 2 plus I square root of 2. And the other residue, the residue of the same function e to the 3 over 4 pi. This is a 1 divided by 2I square root of 2 minus I square root of 2. Okay, these are the two residues, and then you can just add them up and multiply by 2 pi, and you do some computations, and at the end what you get is this is equal pi divided by square root of 2. Okay, this way you can compute the value of this improper integral without computing actually a primitive of this rational function. Okay, and again, this example was a special case of a general class of integrals, and we will call this general class of integrals type 2. So what is type 2? So type 2 is we want to integrate between minus infinity and plus infinity some rational function, r of x in dx, some rational function. And so here r, it's a rational function, so it's the quotient between two polynomials, p and q. These are in general complex polynomials. The important thing is that this rational function has no poles on the real axis. Okay, so we are sure that we are integrating a nice continuous function on the whole real lines. And the other important assumption is that the degree of q should be greater or equal than the degree of p plus 2. So the degree of q is at least 2 more than the degree of p. So this condition is important because it will give us a bound of the form r at z in absolute value. So here we have this degree is 2 more than this, so you get a bound of the form r of z is less or equal than some constant z in absolute value to the power 2. This is again something holding for z large. Okay. Outside of the singularities. Okay, we have this kind of behavior at infinity, and so this kind of behavior at infinity guarantees two things. The first thing, it guarantees that the function r of x is summable on R. Okay? We have power 2, and 2 is bigger than 1, so we have summability, so this integral is well defined. And secondly, it guarantees that when you do, so how do we want to compute this integral? We do exactly as in the specific example. We integrate over this half circle of radius r, centered at 0. And now the contribution on this part, which we call SR, this half circle, the integral of r z dz on SR goes to 0 when r goes to infinity. And the reason is that so the absolute value of this function here behaves as c divided by r squared, and we are integrating on something of length pi r. So when we multiply, we obtain something going as 1 over r. 1 over r goes to 0. Okay, so also this other part works. So the integral on minus infinity infinity coincides exactly with the value of the integral on the contour, and for that we can use the residue formula. Hence we obtain the formula. This is 2pi times the sum of the residue of the function r at zj, j from 1 to k, where the zj's are all the poles of r that are contained in the upper half plane, right here. For zj are poles of r in the upper half plane, so z in c, imaginary part of z, positive. Okay. So we obtain this nice formula for computing the integral of rational functions whenever the degree of the denominator is 2 more, is at least 2 more than the degree of the numerator. What matters are only the poles in the upper part. Okay. So, of course, here you could also, instead of using this contour, you could also integrate on an analogous half circle, but on the lower half plane. You will have to introduce a minus, because then when you integrate counterclockwise, you're actually going from r to minus r, so there will be a minus sign appearing, and in here there will be the residues of your function at poles which are contained in the lower half plane. So if r is a real rational function, there is no difference in these two ways of computing, because so q will be a real polynomial, and hence if q has a 0 here, it will have at z, it will have also a 0 at z bar, so the zeros are symmetric with respect to so the poles of a real rational function are symmetric with respect to the real axis. But instead, if you want to compute the integral of a rational function which is not real, then there might be a difference in the poles, and then it's better to choose the region where you have to compute less, whereas when you have less poles. Okay, this is type 2. And today we conclude with one other class of integrals, namely what we call now type 3. So, type 3 will be an integral of the form integral from minus infinity to plus infinity. Again, a rational function, r of x, but times e to the I alpha x in dx, where alpha is a positive number, alpha is positive, and r is a rational function, so r is the form of polynomial divided by polynomial, p over q. And now the condition is only that the degree of q is at least one more degree of p. So it's greater or equal than degree of p plus 1. Okay. So a weaker condition on the rational function, but again, as before, r should have no poles on the real axis. Okay, this is the integral we would like to compute, and the formula is, so the value of this integral, of x into the I alpha x dx. This is 2pi times the sum of the residues of the function, the whole function, so r of z e to the I alpha z at zj, where again the zj are the poles of r in the upper half plane, where zj are the poles of r in, let's use this notation, h. H is the notation for the standard notation for the upper half plane. Okay, we would like to prove that this formula holds. This integral equals 2 pi I, the sum of these residues. So first of all, notice. So first of all, we need to prove that the improper integral here on the left exists. This function has an improper integral. So we want to show that r of x e to the I alpha x has improper integral. On R. So notice that in this case, this function need not be summable on R, because now the difference in degrees is just 1. So this function might go to 0 when x goes to infinity, only like just like 1 over x. And this does not guarantee integrability, summability. So this function need not, and this has an absolute value of 1, so it cannot help. So this function is in general not summable. However, so this oscillating part will help convergence, and actually the improper integral will exist. So to show this, let's get some space. So what do we need to check in order to be sure that the improper integral exists? We need to look at the integral from 0 to r of our function, r of x into the I alpha x in dx, and we would like to prove that this has a limit when r goes to infinity. Okay? And then we should do the same for the integral between minus r and 0. But the two arguments are completely analogous, so let's just do this case. So we need to show that the limit of this function of r when r goes to infinity exists. So here what we can do is we can do a partial integration. So we integrate by parts by writing now a primitive of e to the I alpha x is 1 over I alpha. So we write r again, and then we have e to the I alpha x. This is between 0 and r, minus integral between 0 and r, the derivative of this, r prime of x. And then again the primitive, there is this 1 over I alpha, which can be written also outside, I alpha. And here we have again e to the I alpha x dx. Okay, so what have we gained when we integrate by parts? So notice that because of our assumption, the function r has a bound of the form r of z is less or equal than c divided by absolute value of z for z large, because the degree of the denominator was at least one more than the degree of the numerator, so we have this bound, and this will guarantee in particular that here in this term when we plug in r, we obtain r at r e to the I alpha r, and this will guarantee that this converges to 0 for r going to infinity. Okay, so in this difference here, the term with r will go to 0, and then we will see the contribution instead given by plugging x equals 0. And here we have an integral from 0 to r, and now the claim is that this function here is now summable. So the function r prime times e to the I alpha x is summable. So, if you know that this is summable, then this will tell us that the limit for r going to infinity of this integral does converge. And then we get convergence of this, so we will get the existence of the improper integral for the given function. So why is this summable? This is, so the absolute value of this is of course just the absolute value of r prime. So what we have to show is that r prime is summable. But r prime is, so r was p over q, and r prime is then the denominator. We have a q squared, and then we have p prime q minus pq prime by deriving the quotient. And now the denominator here, the degree of q squared, is just twice the degree of q. And this is greater or equal than, so degree of q, and degree of q will leave it as it is, plus degree of p plus 1. Okay, because we said degree of q is at least degree of p plus 1. So we get this bound for the degree here. What about the degree of the numerator? P prime q minus p q prime. So this degree is at most, because we would have simplifications here in this p prime q minus p q prime. This is at most the maximum of these two degrees, and these two degrees are degree of p plus degree of q minus 1, because when you derive, for instance here, degree of p prime has degree of p minus 1, and then we multiply by q, so we get plus degree of q, degree of p minus 1 plus degree of q, and here it's the same. We are deriving q, and still we get this contribution minus 1. Okay, so this is an upper bound for the degree of the numerator, and now the difference in degree, numerator and denominator, is at least 2. Here we have plus 1, and here we have minus 1. So the function r prime is summable. R prime has a bound of the form c divided by x, absolute value squared, and this is gives us summability of r prime. Okay, so now we know that our function r times e to the I alpha x has an improper integral, or also one says that the improper integral of this function converges. Also, this function need not be summable. And now we want to use the residue theorem to compute the integral. And this time, as contour, we will use a rectangle. We'll do the following. We will use a rectangle. This is R, this is minus R, and this is I, R. So this is a rectangle of basis of length 2R and height R. And let's call this will be the piece gamma 1, this segment. This horizontal segment will be the piece gamma 2, and this other vertical segment will be the piece gamma 3. And the whole contour will be called gamma. This is a big contour. Now, everything depends on R, but I will not indicate R. So we take this rectangle so big that it contains all the singularities of the poles of our rational function. These are the z, j in the upper half plane. R is so large that it contains this. And again, what we need to show is, now we would like, in order to prove that the improper integral here agrees with the integral on this contour, and hence then by applying the residue theorem to the sum, to 2pi sum of the residue, we just have to show that the integral of our function, the function is f of z, r of z, e to the I alpha z, this is the holomorphic function we're considering now. We need to show that the contribution given by integrating on gamma 1, on gamma 2, or on gamma 3 goes to 0 when R goes to 0. So we need to show that the integral of f of z dz on each of these gamma j goes to 0 when R goes to infinity. And this for j equal 1, 2, and 3. Okay? Again, if we prove this, then this will imply that the integral, the improper integral of the whole real line of our function coincides with the limit for R going to infinity of the integral of the contour, but the integrals on all these contours are the same, provided that the rectangle is so large that it contains all poles in the upper half plane, and hence, residue theorem, you obtain the formula. Okay, so let's first deal with gamma 2. So on gamma 2, z is of the form, this is an x plus e I r, x plus I r, so the imaginary part is I r. And hence, the e to the I alpha z, this is e to the I alpha x times e to the I times I is minus 1, so minus alpha r. And if we take the absolute value of this quantity, this has absolute value 1, so the absolute value is e to the minus alpha r. So if we apply the standard, so we want to integrate over gamma 2, our function r z e to the I alpha z e dz, we like to bound this. So this can be bounded by, so the maximum of the absolute value of this on this line, and for this, to bound this maximum, we can use this bound for e to the I alpha z, and we can also use the fact that, let's write it here, the function R of z in absolute value is bounded by c times the absolute value of z, again for z large, I want to write it. Okay? Because R was P over Q, where the degree of Q was at least 1 more than the degree of P. So here, the kind of bound we take, when we bound R, we take something like C over R. So notice that here, the absolute value of our complex numbers here is at least R, so we get this bound. And then we get the absolute value of this gives us this contribution e to the minus alpha R. And then we have the length of this curve, which is 2 times R. So R and R cancel. And now alpha was by assumption a positive number. So e to the minus alpha R goes to 0 when R goes to infinity. So everything here goes to 0 for R going to infinity. Okay? So this shows that the integral on this horizontal part goes to 0. Now let's work with the vertical parts. Let's do gamma 1, gamma 3 is analogous. So, on gamma 1, on gamma 1, z is of the form, so the real part is R, and the imaginary part is plus I, y, where y varies between 0 and R. Okay? So, the integral over gamma 1 of our function R of z e to the I alpha z dz. So this line integral is nothing else but, so it's an integral in dy. So this is the integral between 0 and R. And here I should write R of small r plus I y. And here, e to the I, so maybe let's compute here what is e to the I alpha z. E to the I alpha z is e to the I alpha r times e to the I alpha I y, so this is I times I is minus 1, so it's e to the power minus alpha y. Okay, so here we get e to the I alpha r times e to the minus alpha y in dy. Okay, I've written explicitly what this line integral is. And now we can bound, put absolute values. And to bound this, I can just bound it by the integral between 0 and r of the absolute value of the function, which is inside, in dy. And for this, I have the bound. So let's recall then integral 0 to r. So the function r plus iy, so it's this rational function here. All these complex numbers here have absolute value at least r. So if we use this bound, we just get a contribution like c divided by r. Okay, this is bounding the absolute value of this. And the absolute value of this, the absolute value of 1 is, this is 1, and the and this is a positive function, so here we have just e to the minus alpha y in dy. Okay? And here, this is now c to the power c divided by r, and I have an integral between 0 and r of e to the minus alpha y in dy. Integral 0 r e to the minus alpha y in dy. Now this alpha is positive, so this function is going to 0 exponentially for y converges to infinity. So this integral, this improper integral from 0 to r converges when r for r going to infinity. So this will converge, so we can also compute it what it is. It converges to 1 over alpha, but c divided by r goes to 0. So altogether this part goes to 0. Okay, so the integral on this gamma 1 goes to 0, the same holds for the integral on gamma 3, and this proves what we wanted to prove. Okay, so this proves the formula for integrals of type 3. So let me conclude with an application of this formula for type 3. The application is, I mentioned before, so in this formula we had a positive, the assumption was alpha is positive, and because of that we integrated in the upper half plane. If you had an analogous integral with alpha negative, what you could do is do the same but consider a rectangle in the lower half plane, and you can check that in that case you would get converging to 0 boundary terms exactly as we did here. Okay, so there is an analogous formula when alpha is negative. Okay, so our last exercise today, for example, example 3, is we want to compute the integral between minus infinity and plus infinity of x sine x divided by 1 plus x squared in dx. Okay, so here we see this trigonometric function sine x. So the natural idea is, of course, to first compute this integral, minus infinity plus infinity x 1 plus x squared e to the I x dx. Okay. Just because we will get then this integral just by taking the imaginary part of this. If we take the imaginary part, this is real, but the imaginary part of e to the I x is precisely sine x. Okay, so we will compute this integral. And this is exactly an integral of type 3. Notice that in this rational function, so we have no poles on the real axis, and the degree of the denominator is 1 more than the degree of the numerator. So we are, and the alpha here is +1, so we are exactly in the assumptions of type 3. So our formula tells us that this is 2pi times, so we have to look at the residues of this function, where at the poles of the rational function. This rational function has poles at I and minus I. These are the zeros of the denominator. So here we get residue of the function z1 plus z squared e to the I z at I, because we're interested only in the poles which are in the upper half. So we have to compute this residue, and this is easily done as this is a simple pole. This residue is 2pi, and the value of the residue, when we factorize the polynomial as z plus I z minus I, and then we still have e to the I z. To compute the residue, we have to at I, we have to multiply by z minus I, so this goes away. And we have to take the limit when z goes to I. So this limit will be I, z plus I, this is 2I. And here we have e to the I times I, which is minus 1. Okay, so this is pi divided by e, and there is still an I in front. I times pi divided by e. So this is the value of this integral, and its imaginary part will give us exactly this integral. So this is the value is pi divided by e. Okay. Notice that the real part of this integral is 0. Here there is no real part, and this is consistent with the fact that on the real part here we will get cosine of x, but then we will get the function that we will, with cosine here, will be an odd function. X times cosine is an odd function, and we are multiplying by 1 over 1 plus x squared, which is an even function, so it's totally it's an odd function, so the interval between minus infinity and infinity is 0. Okay, so the corresponding integral with cosine would be 0, but the integral with sine is this quantity. Okay, so that's it for today, and I'll talk to you later over Zoom. Bye bye.